the Academy of Mathematics and System Science within the Chinese Academy of Sciences. Her research interests include data integration, big data analysis, transportability, survival analysis, and high-dimensional data analysis. Her work has been published in journals such as Technometrics, Biometrics and Statistics in Medicine, and alongside her collaborators, Ying was recently recognized by the American Society for Quality with the 2024 Frank Wilcoxon Award for the Best Practical Application Paper published in Technometrics. And today we're excited to have Ying present on that work. So let's all welcome Ying.
Okay, thank you, Luke, for your nice introduction. And I would also like to thank the invitation and organization for this webinar. Okay, let's start. Good afternoon, everyone. It's my great honor to share our work with all of you today. Today, my talk is about the sequential data integration under dataset shift. And first, I will introduce my collaborators, which contribute a lot to this work. The first is Professor Qin from National Institutes of Cares, and his research interests include biased sampling, empirical likelihood, which we will introduce in our talk. And the second is Professor Huang from University of California, San Francisco, and she is the supervisor when I was a postdoc at UCSF. Here's the outline for today's talk. I will begin with the motivation. Due to the rapid development of data collection technology, researchers can collect big data streams from many sources, as shown in the figure. For example, public transportation, social media, and the production monitoring systems. In today's talk, we're interested in statistical analysis with such large-scale data streams. To reduce the cost of data storage and computation, data can be processed in discrete batches using sequential computing techniques, and we illustrate this method in this figure. As shown in this figure, when we collect data from the first batch, we can calculate the parameter of interest, for example, denoted by S1 hat. This can be the regression parameter estimators in the prediction model, or some other summary statistics of interest. After obtaining hat S1, we do not need to store the individual level data in first batch, and we only store and transfer the initial estimator to the next batch. So when we collect the second data batch over time or from other locations, we can use hat S1 and the current data batch to obtain an updated estimator denoted by hat S2. So in this way, we can update the parameter estimation sequentially by using the current data batch and only estimators from historical batches. So now we will summarize several advantages for the sequential updating method. First, it greatly reduces the cost of data storage and computation. The reason is that for each step, we only store the current data batch and historical summary statistics, but we do not need to store the cumulative data batches, so we can reduce the costs. Second, it protects data privacy and security. The reason is that we only transfer the estimators, summary statistics to the next step or other locations, so we can protect the individual level data. And the third is that the proposed method is highly scalable to large scale data. When developing such methods, the challenge, I think, the most primary challenge, I think, is the dataset shift, which means that the distribution of data changes across different batches. There are many examples of dataset shift, for example, in artificial intelligence or in machine learning. And we will give some examples later when we introduce different types of dataset shifts. So if we ignore dataset shift, then the sequential updating method may lead to biased estimation, poor prediction accuracy, or invalid conclusions. So in our talk, what we want to do is, first, we need to fit a reasonable statistical model to characterize dataset shifts. And second, we want to develop sequential data integration methods to adjust for dataset shifts. Now, let's consider the first point, how to build a model for dataset shift. Before this, we will introduce some notations. And in general, we use Y to denote the outcome of interest, and X is the vector of covariance. Since we consider a case of dataset shift, we need to use different density functions for different batches. In the base data batch, we use FBYX to denote the joint density function, and we use FBY given X or FBX given Y to denote the conditional density functions, respectively. Moreover, we denote the marginal density functions as GBY and GBX. And there are two common types of dataset shifts in applications. The first is covariance shift, where the distribution of X changes over batches, but the conditional distribution of Y given X are the same. Here we give a very simple numerical example. As we can see in two batches, the covariance X was sampled from the different normal distributions. But given X, the conditional distribution of Y given X remains the same across these two data batches. And in real applications, I think kidney transplant data from different states is a good example for covariance shift. In practice, we want to build a model to predict the rejection after kidney transplant using the covariates such as the donor type, living or diseased, or donor age, or recipient age or race. So as we can see from the annual report of kidney transplant, that the distribution of these covariates will change across different states in the United States. But however, the relationship between the rejection and these covariates remains very stable across different states. So I think this is a good example for covariance shift. Now we consider build the covariance shift model. First, as the density functions of X changes, so we use GBX and G1X for covariance shift distribution in different batches. Since they are both density functions, we can rewrite GBX in the blue formula here, and where WBX is a shift function only depends on the covariates. So based on this expression, we can rewrite the joint density in the base batch. FBYX is the product of the conditional density function and the marginal density function. On the covariance shift, the conditional density function FBY given X equals to FY given X. And the GBX can be rewrite in the blue term. And this, the integration equals to 1 because F1Y given X is a density function. So based on this, we can obtain the covariance shift model, which is in blue, FBYX equals to WBX, F1YX. As we can see that on covariance shift, there is only one covariance shift function characterize the difference between the distributions. And next, we consider the prior probability shift, which we may call label shift when the outcome is discrete. In this case, the distribution of Y varies across data batches, while the conditional distribution of of X given Y remains the same. And here is the numerical example. As we can see from the figure that the outcome is binary, so we have two classes. And in different data batches, the probability of Y are different. But given class 0 or class 1, the conditional distribution of X given Y remains the same. So a typical example is the seasonal flu. Suppose we want to build a model to predict flu based on symptoms like cough and fever. During the flu season, I think the proportion of severe cases is much higher than that in the off-season. So this means that the marginal distribution of Y changes across different seasons. However, for given people, the distribution of symptoms is assumed to be very stable across different seasons. So I think this is a very typical example for label shift in practice. And in a similar way, we can build the prior probability shift model. First, we will rewrite GBY as a function of G1Y, where pi by is the unknown shift functions, which depends on the outcome Y. And we can rewrite FBYX as the product of the conditional distribution X given Y and the marginal distribution of Y. So on the prior probability shift, we know that FBX given Y equals to F1X given Y. And GBY can be rewrite as the blue formula. So moreover, the integration equals to 1 because F1X given Y is a density function. So we can obtain the prior probability shift model as shown in the blue term, where the unknown shift functions only depends on the outcome. So in practice, it is very difficult to know which type of dataset shift. So we want to impose a dataset shift model, which is very general. So we consider the dataset shift model in equation 1, where when the shift functions is a product of WBX and pi by. And equation 1 is very general because we can include the commonly correct shift and the prior probability shift as special examples. For example, if we choose pi by as a constant, then we will obtain the correct shift model. And if we use WBX as a constant, then we will obtain the prior probability shift model. So in following, our goal is to integrate data from different batches efficiently while adjusting for correct shift, which is characterized by model 1. Before presenting the proposed method, I think we need to define what we are interested in. For the first data batch, we impose the commonly used exponential family model, which includes such as the normal distribution. And here, beta is the parameter of interest, Fy is a null function, and the forms of functions A, B, and C are known. So the joint density of xy in the first batch can be expressed as in the blue formula. So we're interested in the first batch, which means which refers to the reference or the target population of interest. So as time goes by, we can collect more data batches. So in the base data batch, we consider the dataset shift model, which is which is presented in equation 2. And here, for model identifiability, we assume that these two integrations equals to 1, because if we multiply a constant, then the dataset shift model will be the same. So we impose the we assume that the integrations equals to 1. So I think that in practice, the base data batch may shift because due to many reasons, such as maybe as time goes by, the study designs diverse, and there may be some changes in environmental conditions, for example, such as the temperature and the weather, and also in telemetrics, they may have some equipment wear. So that's why we need to deal with the dataset shift, I think. Also, based on these notations, we also need to introduce some notations for the observation. Since we have different data batches, so the notation may be a little complicated. And we use YBI and XBI to denote the outcome and covariance of a subject in the BIS data batch. And the sample size is NB. And we use DB to denote the BIS batch. It includes both the outcome and the covariance. And we also define a notation for the cumulative data up to the BIS batch, where the capital B means up to the BIS batch and the C denotes cumulative. And we also define the cumulative sample size. And we use beta hat B to denote the proposed updated estimator of beta up to the BIS data batch. Okay, now we will start the data integration procedure. When we collect the first data batch, the initial estimator can be estimated use the maximum likelihood estimator, which is denoted by beta hat 1. And it is easy to see that beta hat 1 is asymptotically normal. So we can use the first data batch to estimate the asymptotic covariance matrix, which is denoted by sigma hat 1. So as I think we need to recall the sequential data integration procedure in our mind. So our goal is to obtain beta hat 2 and sigma hat 2 using the historical summary statistics and current data batch on the dataset shifts. So the first question we need to deal with is that how to utilize information in summary statistics. Okay, now we recall that beta hat 1 is normal, is asymptotic normal. So we can treat beta hat 1 as a realized as an observation from the normal distribution where the mean is beta 0 and the covariance matrix is sigma 1. So in this way, we can obtain the log likelihood based on the asymptotic normality of beta hat 1, which is summarized using equation 3 here. Now, the second question is how to utilize information in the current data batch. Because we need to deal with the dataset shift here. So summarizing information in the current data batch is much difficult. Because actually, in general, we may consider the log likelihood, but as we can see in the blue formula here is that we have an unknown shift function pi to y and unknown parameter beta in this term. So it is very difficult to handle this term or estimate this term. So to tackle this problem, we borrow idea from Liang and Qin, 2000. Here, Qin is my co-author, Professor Qin, and we consider the log pairwise pseudo likelihood. The formula is very complicated, so I think we need to only care about the blue term here. What does the ratio mean? It means that we do not consider the conditional distribution of y given x. We consider this conditional distribution of yi, yj given xi, xj, and the order statistics of yi and yj. This is a very smart technique, I think. So when based on the work from Professor Liang and Qin, we can summarize the information using the log pairwise pseudo likelihood. And fortunately, we can see that by using the ratio, we can eliminate the unknown shift functions, and only the unknown parameter beta is involved in the objective function, and which way is denoted by equation 4, the log pairwise pseudo likelihood. So I think we do not need remember the details or figure out the details, but I think we only need to remember that, okay, if you cannot deal with the conditional distribution of y given x, you may consider about the conditional distribution of y given x and order statistics, and maybe you can eliminate all the unknown shift functions. So we have addressed the second question. Now it turns to the third question, is how to combine information from these two batches. In a naive way, I think we can estimate beta by maximizing the sum of two objective functions. And of course, we need to adjust for sample size. So as shown in equation 5, the first term is the log pairwise pseudo likelihood, and the second term is the log likelihood based on the asymptotic normality. But I think the problem here is that, as we all know, if we have two independent data sets, then the sum of log likelihoods is the efficient way to combine information. But in equation 5, the second term is the log likelihood, but the first term is not log likelihood. It's log pairwise pseudo likelihood. So I think if the equation 5 is not an efficient way to combine information from two batches. So our next question is how to improve the efficiency. And also we can ignore some mathematical details and only focus on the blue as the blue formulas. First, S2 beta is the first derivative of L beta D2 with respect to beta. That is the score function of the log pairwise pseudo likelihood. So based on the score function, we can establish the asymptotic normality. And here, the covariance we can estimate the covariance matrix used the data. So based on this, we can also construct the log likelihood based on the asymptotic normality of the estimating function S2 beta, which is summarized in 7. So in this way, we can obtain estimating equation of the objective function in equation 8, which is a sum of two log likelihoods. So I think when we consider the sum of log likelihoods, I think it is an efficient way to combine information from different batches. So in this slide, we will make a detailed comparison why the proposed estimator is more efficient. As we can see from equation 6, that the naive updated estimator is the solution of equation 6, which is the first order condition of the objective function 5. And the updated estimating equation is the solution to equation 9. So the difference remark highlighted in blue. As we can see that in equation 9, we use inverse of the covariance matrix. What does this mean? It means that, okay, if I think S2 beta is very stable and with a small estimation uncertainty, so the covariance matrix is small. And the inverse of covariance matrix means that I put more weights on this estimating function. But if S2 beta has large uncertainty, which means that, okay, this estimating equations is not stable. So the covariance matrix is large, and the inverse of covariance matrix means that we put small weights. So based on this comparison, we can see that the proposed estimator enjoys an efficiency gain by solving a weighted sum of two estimating equations from the two data batches. So in practice, I think to improve efficiency means that we can obtain accurate estimates with smaller sample sizes. Thereby, I think we can reduce the costs in data collection. So also, we can have some theoretical analysis and prove that beta hat 2 is asymptotic normal, and we can update the estimation of the covariance matrix. So for general data batch, we can update the estimation of beta using the historical summary statistics and current data batch by maximizing the augmented log likelihood. And as we can see in the formula, the augmented log likelihood is a sum of two likelihoods. The first term is derived from the current data batch, which is the log likelihood of the asymptotic normality of the estimating equations. And the second term is derived from the historical summary statistics based on the asymptotic normality from the summary statistics. So I think this is an efficient way because we make a sum of the two log likelihoods. The large sample property of the proposed estimators is summarized in theorem 1, and I think we only remember that the proposed estimator is efficient because, as shown in the blue term, the convergence rate depends on the cumulative sample size, which means that we do not need to store all the individual level data, but we can reach the same convergence rate. So it is a good estimator, I think. And also we prove that beta hat B is asymptotically more efficient than the naive updated estimator. And based on the asymptotic normality, we can estimate the covariance matrix denoted by sigma hat B. So based on the estimators, we can make a statistical inference for the distribution we are interested in. In the previous, we only care about the first data batch, that is the reference of the target population. So we only estimated the parameter beta. But in some applications, we may also interested in the data set shift patterns across the batches. If we can estimate all the shift functions, then we can make inference for every population. So, but unfortunately, even we have tried a lot, but we cannot achieve this goal in a general dataset shift model. But we can achieve this under the prior probability shift model. So in the following, we only focus on this model in equation time, where the shift is characterized by pi by, which is a shift function only depends on the outcome. That is the label or the prior probability shift model. So in the following, our goal is not only focus on the parameter beta, but we want to obtain updated estimation of beta and evaluate the prior probability shift model at the same time. So to avoid confusion, we use a different notation for the updated estimator. We use beta tilde B. And the historical summary statistics can be utilized in the same way. That's the asymptotic, based on the asymptotic normality of beta tilde B -1, and we can construct the log likelihoods. So I think we need to handle the question is that how to utilize information in the current data batch, because in the previous section, we use the log pairwise pseudo likelihood. So the objective function only involve beta, but do not contain any information about data set shift. So I think we need to use a new objective function. The way to solve this problem is that we utilize information in the current batch based on the full likelihood, which involves both beta and pi by. And recall that we assume this integration equals to 1 for model identifiability. So if we define HBY is a product of pi by and Fy, this function behaves like a density function. It's positive and its integration equals to 1. So we call it a synthetic density function because actually it looks like a density function, but we do not have observations from this density function, from this distribution. So based on this notation, we can rewrite the joint density function in the current data batch at byx. So we can omit the details and we only focus on the blue term and the green term. The blue term is the synthetic density function we defined, and the green term is an integration. So as we see in the first, we consider the green term here. As we see, it is expectation with respect to G1x. G1x is the marginal distribution of x in the first data batch. So this integration actually is the expectation of the exponential term. So if we store the covariance data in first batch, then we can estimate the green term use the empirical version. This is a function of y and beta. So this is the first step. And the next step, we will consider this term, which is here. So when we approximate this integration, we can use equation 11. Because the green term, the integration in green is approximated using phi y beta. So when we pose the weights PBI at each jump, at each observation YBI, then we can approximate this integration use a sum of PI phi y and at each data point. So this is based on the approximation of the integration here. So I think the key point here is that we borrow the idea from empirical likelihood. And a very simple example for empirical likelihood is the empirical cumulative distribution function, which we assign weight 1 over n for each observation where n is a sample size. And in this case, we assign weight pi for each data point. So the integration is a sum of with the weight pi. So here, based on the equation 11, then we can obtain we can approximate the log 4 likelihood. The expression is very complicated, so I think we only need to remember that when you need to deal with some unknown functions, and the functions can be re-expressed as a density function, then you can think about application of the empirical likelihood methods. You can use divine weight here and approximate the integration use the weighted sum. And based on the log 4 likelihood as shown in the first term, and the second term is used to summarize information from historical summary statistics, we can obtain the sum of 2 log likelihoods, and we estimate the unknown parameter beta and p with the weights p by maximizing the sum of 2 log likelihoods. And we need to care about the constraint here because the weights is positive, and since it is the weights of the synthetic distribution, so the sum of the weights equals to 1. And after some tedious calculations, we can obtain the result estimators, and we denote it by beta tilde b and p tilde bi. Since p tilde bi is the jump of the cumulative distribution function, so we can estimate HBY use the following expression and denoted by H tilde by. So based on H tilde by, as we can see, we can evaluate the prior probability shift. And theorem to summarize the large sample property of the proposed estimators, and we need to pay attention to the convergence rate. First, beta tilde b, the convergence rate depends on the cumulative sample size. This is reasonable because we borrow information from the cumulative sample size about data. But based on we have different prior probability shift functions for each data set. So the current data batch, so the prior probability information is only provided by the current data batch, and thus the convergence rate for H tilde by is only depends on the current sample size. So as we can see that we have H tilde by, so we can use this estimator to check the prior probability shift for a given pi0y. For example, if you specify pi0y as a constant, it means that you assume there is no prior probability shift. So if we want to check the non-hypothesis, we can consider the difference between the estimator and the cumulative distribution function under the non-hypothesis, and then take the super over y. In applications, I found that it is very difficult to determine the critical value for these test statistics. From my numerical simulations, I think that maybe bootstrap can be used to approximate the non-hypothesis distribution. So this slide is a summary of the proposed methods. As we can see that when we collect the first data set, we can calculate the log likelihood and obtain the MLE as the initial estimators. And when we collect data set shift onto when we collect data on the data set shift, then we can calculate the log likelihood sequentially. How to calculate the log likelihood? It depends on your purpose. If you're only interested in the regression parameter beta, then you can use the first method, the proposed balance. And if you are interested in both dataset shift and the regression parameters, then you can use the idea of empirical likelihoods. So when we obtain the log likelihoods, we can make a sum of two log likelihoods to update the proposed estimators to obtain the proposed updated estimators sequentially. So finally, we can obtain the proposed estimators. So in this unifying the sequential data integration framework, I think we have some advantages. First, we impose a dataset shift model, and this model can characterize two commonly used dataset shift patterns of dataset shift. And in our framework, we only store and transfer historical estimators, so it can protect data privacy and security, and it can greatly reduce the cost of data storage and computation. Next is a simple numerical study. In the first data batch, we assume we have three estimators already. Is X3, and the first is the normal, and the X2 and X3 are binary, and the X4 is the interaction term. So given X, we assume that Y follows the normal distribution, and this is the true regression parameters. The sample size of the first data batch is 800, and in the sequential data batches, we consider both prior probability shift and dataset shift. First only depends on Y, and the second type of dataset shift depends both on Y and X1. And the sample size of each data batch, we only assume 200. And this is the result under prior probability shift. Beta hat 1 is the MLE using the first data batch, and beta hat B is the proposed estimator under dataset shift, and beta tilde B is a proposed estimator under prior probability shift. So as we can see that in all scenarios, the bias is small, but by integration, by integrating data from the sequential data batches, the proposed estimator, the standard deviations are much smaller than beta hat 1. And this is the results under dataset shift scenario. As we can see, because beta tilde B can only handle the prior probability shift. So when we include when we integrate more data batches, beta tilde b, the bias of beta tilde p can be very large because it cannot handle the shift contributed by x1. But the proposed estimator beta hat b, the bias is small and the standard deviations are much smaller than beta hat 1, which means that we can improve the estimation efficiency. Okay, finally, we will introduce the real data example here. And I was a postdoc, I lived in the Bay Area, so I downloaded the dataset of Ford GoBike bike sharing data. And I think it is important to predict the trip duration time because it depends how much you pay for your trip. And also we want to achieve a balance between the user demand and the limited sources. But actually, as we can see that in practice, factors may be such like the weather conditions, raining or sunny, or trip purpose. You ride your bike for work, for holiday, or for go to school, or if whether you join the membership programs, and the other factors that will introduce dataset shifts. So I think the proposed methods, it can be applied to analyze such data set. And we download the data. The data collects bike sharing recorded in January 2019 and more than 146,000 rides observations. And we're interested in the trip duration time, but the trip duration time is always positive. So we take a log transformation as the outcome y. And we consider 4 covariates. The first is the age, and the second is participants participate in the bike sharing for all program. This is a program for the members. They have some benefits. For example, in the first hours, it is free for who join this program. And the third covariate is the trip start time. It is a binary covariate, 7 a.m. to 7 p.m. or others. And we also consider the interaction time between age and the program because as I checked from the website, join the program, there have some requirements on the age. So I included the interaction time here. And since we have data in the January, so we can divide the data set into 31 batches according to the date. And the first data batch consists of more than 1,000 observations. And in the first data batch, we're interested in the first data batch, which is the New Year's Day. And we assume that given X, Y follows the normal distribution. First, we check this normal assumption. We compute the residuals using the first data batch, and here is the histogram of these residuals. And as we can see from the figure, it looks like follow the mean zero normal distribution. So we also do a model checking, and the p-value is 0.162. So we do not have evidence to reject this assumption. So I use this normal assumption in our analysis. And this table summarizes the estimated regression coefficient. And the first 2 columns is the MLE using the first data batch. And the middle columns is the proposed estimator on the dataset shift, and the last 2 columns is the proposed estimator on the prior probability shift. And the SEE is the standard error estimates. So let's see the blue numbers. As shown in the blue numbers, we can see that the coefficient estimates of program and start time is quite different from the maximum likelihood estimator in the first data batches. So I think this result indicates that maybe the distributional shift across different dates may depend on not only on the duration time, but also depends on some covariates. And next, let's focus on the red numbers. And as we can see from the red numbers, the adjusted effects of age and the start time of the trip are statistically significant when applying the proposed method. But as we can see from the first two columns, the adjusted effects of age and start time are not statistically significant. So this means that by combining information from different batches, we can improve the estimation efficiency and we can construct more accurate confidence interval. And here we also plot the coefficient estimates, and the solid line is the coefficient estimates for each data batch, and we also include the point-wise confidence bands of the regression coefficients, which is shown in the dashed lines. And as we can see that when we combining more data from batches, and the confidence bands can be narrow, and we can construct more accurate prediction. And finally, we have some discussions, and the first is proposed by the reviews. And I think in practice, sometimes maybe we collect data in discrete batches, but sometimes we need to divide the data by ourselves. And I think we can first divide the data based on some prior knowledge about changes in data distribution. For example, maybe some changes in the weather or the environmental conditions. And second, I think we can divide the data based on our storage memory limitations and computational resources. And another question I think is most interesting is that in today's talk, we assume that covariates are the same across different data batches, but they only have different distributions. But in practice, due to the development in scientific knowledge or data collection technology, I think in some applications, new covariates may be added during data collection. For example, in medical research, we may have some new medicine or some new treatment, and then in technological applications, we may have some new equipment. So I think to build more accurate prediction models, we need to include these new covariates in our prediction models. But how to characterize the distributional shifts? It is very difficult because we do not have these covariates in the past batches, in the previous batches. So I think this is an interesting topic, but now I have no ideas about this. And also here's the reference. And this is the end of today's talk. Thank you very much for your attention. I'm happy to take any questions or comments. Thank you.
Okay, well, thank you, Ying, very much for this excellent talk. If anyone does have questions, please feel free to write them in the chat, and then we'll convey them to Ying. I guess while we're waiting for others to ask questions, I might start with asking a question myself. So you talked about, and you mentioned this a little bit at the end of the talk, but you focused on covariate shift and the prior probability shift in this work. Are there other types of shifts that you think you could address in future work, or would those types of shifts just be so substantial that maybe it doesn't make sense to combine the data from different batches?
Yeah, actually, in our recent work, I'm interested in the domain shift, because sometimes due to the limitation, we can only sample a subset, but we want to extend our results to a more bigger populations. For example, if sometimes in our talk, we assume that the support of the covariates X are the same, but in practice, sometimes maybe we only have the data from the younger patients or the older patients, but we need to extend our results to patients with a wide range of ages. So I think this is a very interesting topic here. So, so far, I think the proposed method cannot do such type of data set shift, because as we can see that here, when we propose the model, for example, in here, when we propose the model, as we can see that we need to assume the support are the same. But if the support are not the same, I think we cannot deal with. Yeah, so I think this is a very excellent question, but so far I don't know how to handle more general types of shifts. Yeah, thank you.
Thank you. Yeah, and I guess I'll ask another question just to give anyone else potential time to pop another or comment in the chat. But so the prior probability shift, you were estimating these distributions conditional on the response Y, right?
Yeah, it depends on the definition is in the book. Here, in this book, he defined different types of data set shifts, but I summarize the definition using mathematical formulas. Yeah.
Okay, so let's say you're conditioning on a continuous covariate, I guess the logarithm of the bike trip duration was continuous, right?
Yeah.
Do you have to do any discretization to compute those conditional distributions?
Oh no, the proposed model and the proposed method can handle the continuous outcome, but for show the prior probability shift in a figure, I think the binary outcome is easy to show, because it is difficult to draw a picture for continuous outcome. Yeah, actually, I think we can, as we can see from this formula, actually, I think prior probability shift means that if you sample the observations from a population, the sample is not a random sample. The sample probability depends on the outcome. I think another, let me think example for the continuous outcome. Okay, when we take a survey about the income, and we want to build a model about the salary, and the covariates, maybe the education and the age and the gender. So sometimes when I ask someone, well, what is the salary? But maybe if the salary is really extremely low or extremely high, he may not tell me. Yeah, but sometimes someone they think that it is not a problem, and they will tell me the exact number. So I think when we sample the data for predicting the salary or the income, I think maybe it is a bias sampling problem, and we need to deal with the prior probability shift, because I think whether you can sample this data depends on the salary. I think the high salary and the low salary, then maybe they will not tell you the income, I think. Yeah.
Makes sense. Well, thank you, Ying. I don't see any other comments in the chat, so I think we'll
Okay.
wrap up the webinar now. Thank you again for taking the time to present on your work. We really appreciate it. Yeah, and I hope everyone, all the participants, thank me or join me in thanking you for your time. And I'm sure if anyone else has other questions, they can reach out over email.
Oh, okay. Thank you. Thank you for the invitation and organization. Okay.
Yeah,
Bye.
thanks, you.
Mm.